My name is Daniela and I'm a PhD candidate at Rice University. In this video, I will show you how I use machine learning in my job market paper. In a nutshell, I examine the economic forces that impact the level of softness and hardness in the language of corporate disclosures. I use the text from the MD&A section of 10-Ks to construct a multivariate measure of softness and hardness that aggregates measures of vagueness, tonal content, forward-looking, numerical intensity, specificity, historical content, and objectivity in the language of textual disclosures. In this video, I will focus on the last linguistic attribute, objectivity, and I'll explain the algorithm I use to measure it. To quantify the degree of objectivity in textual disclosures, I develop a machine learning algorithm that classifies sentences as objective or subjective based on the narrative structure of the sentence itself and its linguistic properties. Specifically, I implement a supervised model that learns patterns from labeled sentences and generalizes to new data that has not been seen before. Thus, the model is able to predict the objectivity of sentences that were not used during the training process. After completion of the training phase, I use the optimized model to predict the probability of each sentence being objective in the unlabeled sample. The first step is to gather labeled data to feed to the model. So I start by randomly selecting 3,000 sentences from the MD&A section of 10K filings from my sample. I manually classify each sentence into an objective or subjective class according to whether the information provided is based on facts or on opinions that may be subject to interpretation. Here are some examples of the sentences that I classified as subjective versus objective. For instance, the first sentence, our products are distributed in the United States and in over 20 other countries, is subjective because it presents factual and verifiable information. In contrast, the sentence, our losses, while greater than projected, were still modest considering the magnitude of the economic storm, is subjective because it is based on an opinion and a particular interpretation of an event. My classification task results in about 60% of the sentences being classified as objective and 40% as subjective. Now that I have labeled data to learn from, I must decide how to analyze it. Given the recent advances in deep learning algorithms and the recent success in natural language processing, I used a neural network to analyze my data. But before getting into the details, let me give you a brief background on neural networks. This graph shows the structure and workflow of a basic neural network. In the first step, vectors representing the textual data are sent as input to the first hidden layer of the network. Each layer comprises a set of processing nodes or neurons that are densely interconnected and that assign weights to each piece of information received. Depending on the chosen weights, each layer transforms the data received and passes the relevant information to the following layer. The last hidden layer transforms the data into predictions that can be compared with the true targets or labels of the sample using an appropriate loss function for the task. The loss function produces a loss score that is then propagated back into the beginning of the network and used by an optimization algorithm to modify the weights and create predictions closer to the true targets. The process ends when the estimated predictions are close enough to the truth and the accuracy goals specified by the researcher are reached. Let me begin by describing the simplest possible neural network, one which comprises a single neuron. This neuron takes as input x1, x2, x3 to xn and outputs y hat. The operations inside the network consist of a linear transformation of the inputs using weights w and an activation function g. This model could be used for a simple classification task. But what if our data is more complicated and the classification task is not that straightforward? In that case, we can actually combine models to address the complexity of the task. For instance, in this graph, we can combine the two simple linear models in the left to create a nonlinear model that better fits the data. In fact, We could even add weights to each model in order to prioritize one over the other and improve our results. In essence, we would be creating a model that receives as input the output from previous models. This is basically the idea behind neural networks or multi-layer perceptrons. Take a look at the following multi-layer network. This network has an input layer consisting of x1 and x2, a hidden layer, and an output layer. As you can see, neural networks can have multiple output units, like in this example, and they can vary in the number of hidden layers and the neurons in each layer. Now, very complicated neural network architectures can be very powerful, but they can also be very inefficient and very computationally expensive. Now, let me get back to measuring objectivity in corporate disclosures. For my particular task, I use a special type of neural network called recurrent neural network, which is a model capable of learning dependencies among sequences of words and is widely used in computational linguistics. Now, this figure illustrates the structure of a simple recurrent neural network. In the diagram, layer A receives input xt, sends information to itself, and then outputs xt. If we unroll this network, we can see that each piece of information received at each step is transformed inside A and then passed to the following step to serve as part of its input. This way, the network keeps remembering the context of the information received. Now, at this point, my data looks something like this. Basically, I have a collection of sentences and labels where the label is equal to 1 for an objective sentence and 0 otherwise. And I need to transform this textual data into vectors of numbers. To do that, I use word embeddings, which are numeric representations of text that are meant to map human language into a geometric space. This geometric space reflects the semantics relationships in language by assigning similar vectors to words with similar meaning. In addition, word embeddings capture semantic relationships among words as illustrated by the positioning of the words from the following picture. In the left panel, the vectors representing words are positioned to follow gender relations, while the right panel shows the plural singular relationships of text. Notice that the distance from the vector man to woman in the left is the same as from uncle to aunt or from king to queen. In the right panel, the vectors kings and queens are analogous to their singular form king and queen. With these word representations, it is possible to perform operations with words that capture semantic relations, such as king equals woman plus queen minus man. The analogy feature also works for other types, such as adjectives, grammatical tenses, etc. Now here I am loading the vocabulary from my sample of MDNAs, which includes almost 5,000 words. Using the embedding matrix from Globe, I include each word into an index that points to a specific entry in the matrix. For instance, the sentence, "I do research in accounting," would be coded into the following indices and vectors of numbers. Now recall that these numeric vectors come from a pre-trained model that captures semantic relationships in a high-dimensional space. So this transformation retains the properties of the text, such as its context and grammatical structure. But now we have it in a format that can be fed into the model. The next thing I do is I split the dataset into the train, validation, and test samples. The validation sample is basically used to provide an unbiased evaluation of the trained model, and with this, fine-tune hyperparameters such as the number of hidden layers in the network or the learning rate in the optimization algorithm. Now, to train the model, I use a particular type of recurrent neural network called long short-term memory network, which specializes in remembering relevant context from long-term sequences and at the same time forgetting irrelevant short-term information. In the model, I use bidirectional layers because it typically increases accuracy and mitigates forgetting issues. Bidirectional layers present the same information to the neural network, but they do so in the opposite direction. I also add an attention layer, which consists of an attention mechanism that allows the network to evaluate relative contributions of each word after seeing the entire sequence, and with this to focus on the words that are the most relevant in the classification task. Now let's put the model together. First, we convert text into numbers using word embeddings. Next, we process the embeddings through the long short-term memory layer. Then we use the attention mechanism to reduce the sequence into a single vector of numbers. And last, we map this vector to a probability space using a binary classifier. I use binary cross-entropy loss function as my objective function and the stochastic gradient descent algorithm to update the parameters. And I do this through the algorithm called backpropagation. Also, in order to avoid overfitting my training sample, I add an LT regularization term and I use dropout. Now, after training for 100 epochs and based on the performance of the validation sample, the model fitted during epoch 52 achieved the highest F1 score in arrow symmetrics. The arrow symmetric shows that the model has a good fit. According to Kim and Skinner, the model has an outstanding discrimination ability in the trained sample and an excellent ability in the validation sample. When I evaluate the trained model and the test sample, it achieves an accuracy of 87 on the classification of objective sentences. I then use this model to predict the labels for the rest of my sample sentences from the MD&A sections. Now, in the last part of the video, I want to show you what the predictions will look like for a couple of sentences. For instance, I have a sample of 4 sentences here. My model classifies the first and third sentence as subjective and the rest as objective. We can also look at the results of the classification task in terms of the probabilities of the sentence being subjective or objective. As you can see, the model somewhat struggled to classify the third sentence, perhaps because it is shorter and has less information. However, it correctly classified it as subjective. Last, I want to show you a visualization of the attention mechanism. Recall that I'm using an attention layer that identifies the words that are the most relevant to classify a sentence into objective or subjective. While the first sentence in our sample was classified as objective, the attention mechanism seemed to consider all of the words in the sentence. However, if we look at the next example, which is a subjective sentence, you can actually see that the attention layer focused on qualitative words, such as difficult and belief. In the third sentence, the model paid attention to the phrase "we fully utilized," which contains a verb in past tense and may be a hint that the information is a historical fact or some verifiable claim. Lastly, the fourth sentence was also classified as subjective, and here the model identified "we believe" and "will be sufficient" as key phrases to classify the sentence as subjective. For more details on the methodology of my paper, please see Appendix D of my job market paper. I will also make this notebook available in case you want to look at it again. I hope this video gives you a quick overview of how machine learning can be applied to analyzing corporate data. Machine learning algorithms are a remarkably powerful and efficient approach to analyzing high-dimensional data. These techniques are able to identify the grammatical structure of sentences and semantic relationships in text. I believe that by incorporating these tools into accounting research, we can actually broaden the collection of signals that we study, and with this develop a richer understanding of the corporate information environment, the consequences of disclosure regulation, the incentives behind disclosure choices, and the implications for capital markets. Thank you for watching.